Hello, all. I just wanted to introduce the new chapter today. We should have all just taken our quiz on the periodic table and the atomic structure. So I wanted to um, introduce what the new topic is, and um, hopefully we can get to do a little bit of practice on this. I apologize, it's a little bit echoey. I just moved into a new house over the weekend, so I don't have any pictures or furniture in my office yet, so it's real. Sorry about the sound quality here. Um, so, in the last chapter, we talked about the structure of the atom, and we talked about kind of what makes one atom different from another, the protons, and then we started talking about the electrons around the outside of the atom and the Bohr model and things like that. Um, so, what we want to start talking about now is how atoms bond with each other or how they connect to each other. And so, the question kind of that drives this whole chapter is, what do you think the part of the atom is that interacts with other atoms? So if one atom is bonding or connecting to another one here, what is actually doing the connecting? And the answer is it's got to be something on the outside of the atom. It's got to be the electrons. The electrons are the things that are um, doing that interacting because they're so far outside. The things on the edge are doing the interacting. And one thing we have to think about are the valence electrons. Remember, the valence electrons are on the very outside. So if we have concentric rings of electrons, the valence electrons are always in the outermost ring. Regardless of how many energy levels there are, the valence electrons are always in the outermost ring. Okay? So this is what we call the Bohr model, drawing them like this. And remember, we always completely filled the rows underneath, completely filled the shells underneath with electrons, and the outer ring, the valence ring, might be partially full. Okay, so here's an example of lithium, phosphorus, chlorine. They have different numbers of valence electrons because they are in different parts of the periodic table. As you get closer and closer to the right side of the periodic table, you're adding more and more electrons, and you're filling up this last ring. And once it gets full, chlorine doesn't have a full one, but if it did get full, then you'd be a noble gas. You'd be at the end on the complete right side of the periodic table, and then you'd need to add another ring over top of it. Okay, so remember that's kind of how that worked. So the valence electrons, you can always figure out the number of valence electrons, and this is going to be important for later on. You can always figure out the number of valence electrons by the last digit of the group number. So remember here, lithium's got one valence electron because it's one in the last row. Phosphorus has 1, 2, 3, 4, 5. Chlorine has 1, 2, 3, 4, 5, 6, 7 in the last row. Okay, so if we look at a periodic table with the groups numbered, you can see, okay, group 1, all of these elements are going to have one valence electron. Group 2, these are all going to have two valence electrons. So I wrote in an example here. Magnesium is in group 2, second column, so it's going to have two valence electrons. We don't really count these middle 10 columns for bonding purposes. And so usually, when you take chemistry your junior year, we get a lot more in depth about the transition metals and the rare earth metals, what they're doing. But then we can also say that once we get over to the right side of the periodic table, it's a little bit easier, especially with the first couple rows, to consider that there are 7 valence electrons in the 17th column. It just makes our bonding rules a little bit easier to do. And I know that that's slightly different from what we thought of with the Bohr model, because you might be thinking, well, shouldn't iodine then have 17 valence electrons? But it's a little bit easier to think about it as 7 for a very specific reason, and we'll talk about that a little bit more in depth later. But for now, let's just kind of think about these top couple rows would follow that trend perfectly, so we'll kind of be thinking about them for now. We also kind of talked about how atoms want to have 8 electrons, and this is somewhat new, but this is a key idea that we've already mentioned before. The octet rule is just a rule that states that atoms tend to want to have 8 valence electrons. Okay, so that means that if it has nearly 8 electrons, it wants to gain enough to get up to 8. And if it has only 1 or 2 electrons, it wants to lose electrons to get down to 8. The exception is hydrogen and helium can only fit 2 electrons in their first ring. So if we go back to the periodic table, like hydrogen only has 1 electron to lose, and it can only gain 1 more in that level to get over to helium. So, but all the other ones we can consider that it's kind of like 8 across. Kind of a visual example of what the Bohr model is doing for this. So sodium is in group 1. Sodium has 1 valence electron. It has 11 electrons total, but it has just sort of this dangling electron to make the 11th one. It has 11 protons on the inside, and it has this 11th electron here that it really doesn't want that much, because it would be much happier having a full shell of 8 as its valence shell. So what it does is it loses that electron very commonly and becomes a positive ion. Remember, it's still got to have 11 protons in here, but if it has 11 protons and only 10 electrons around the outside, it's going to have a positive charge overall. If we look on, so that was kind of give you examples. So that was sodium here. Fluorine, on the opposite side of the periodic table, is almost full. Okay, so if we look at fluorine's Bohr model here, fluorine normally has 7 valence electrons, but it wants to get an extra electron to make 8. So it frequently adds in another one. And remember, all fluorine atoms only have 9 protons. If they had a different number of protons, they wouldn't be fluorine. So when it gets that extra electron, it becomes a negative ion, because it still keeps its 9 protons, and then it has 10 total electrons, 8 in the last shell, 2 in the middle, or in the first shell. Okay, so all this to say that there's lots of different possible charges for atoms. Atoms frequently become ions. We've talked about this a couple times already. So adding and losing electrons help atoms form bonds, one of 2 kinds of bonds. A chemical bond is when atoms sort of physically join together. They kind of get connected. And I think we've sort of thought about this in other ways before. Frequently when we think about chemical bonds, we kind of draw like a line between 2 atoms, right? So like a chemical bond is whatever's happening to make those 2 things stick together. Okay, so there's really 2 different camps for these, and one of them we're going to talk about a lot more than the other. But an ionic bond is the first type. I'm going to make this a little bit bigger. An ionic bond is when 2 oppositely charged atoms attract each other. Okay, so again, charged atoms are ions. Okay, so that's the first kind of bond we're going to talk about, ionic bonds. And so we're just talking about ions. Covalent bonds are a little bit different. So covalent bonds are something that only certain kinds of elements will even do. Only nonmetals will form covalent bonds. So covalent bonds are when you have, so we see the words co, like together, and valent, like valence. So this is when atoms share valence electrons. Okay. So that's sort of a different sort of bond entirely. But we're going to talk mostly about ionic bonds here. So ionic bonds, you have some elements want to gain electrons and some elements want to lose electrons. So we can remember from our last chapter that really there's just 2 different kinds of elements, and one of them is what forms the positive. Well, remember, the metals form the positive ions. Oops, it's making me write white on white here. Oops. So the metals form the positive ions, and those are the cations. Okay, so metals are always wanting to lose electrons. Those are the things on the left side of the staircase. So elements over here, so there's the staircase, elements over here want to lose electrons, so they're always forming positive ions. Elements on the right side are nonmetals, want to gain electrons. Okay, so if they gain electrons, they have to form negative ions, which we call anions. So here's the idea. In order to have two oppositely charged things attracting, you always have to have a metal and a nonmetal. We talked about this when we did the flame test, how we always have both of those in an ionic compound. So if you look at the periodic table, every ionic bond is something on the left side of the staircase paired up with something on the right side of the staircase. Okay, so you have some of these things over here and some of these things over here. Okay, so you could make any combination you want. You could make zinc and oxygen. You could make strontium and nitrogen. You could make sodium and fluorine. You could make lithium and iodine. Excuse me. It's dusty in here. So you can make any combination you want. And I wanted to just briefly explain how you name those things was my goal today. Okay, so the rule is for naming an ionic compound, since you always have a positive and a negative, the rule for naming ionic compounds is that if it's just two elements in there, a negative one, so you always have a positive one first, and then a negative one. The negative one is going to always end in "ide" if it's just an element, if it's just a nonmetal by itself. So if I had a nonmetal like chlorine, I don't call it, so we know an example of this would be sodium chlor. We don't call it sodium chlorine, we call it sodium chloride. So the second name, the nonmetal name, is always going to change to "ide" at the ending. So the negative ion, the nonmetal, always changes to "ide" at the end. So ones that people tend to mix up are oxygen and nitrogen, because people want to say like oxygide, but it's really oxide. It makes more sense. Or nitrogide. Nobody says that. The right way of saying that is nitride. So I'll do a couple examples for you here, and I think you'll figure out how to do the homework from this. So the subscripts don't change the name for ionic compounds because there's only one way to pair up a positive and a negative. So you don't need to think about the numbers at all for now in terms of naming. So I'm not going to. So sodium chloride is NaCl. CaF2 is calcium fluoride. I'm not going to call it difluoride or anything like that. I just call it calcium fluoride. So I'll do a couple examples here. So we just did sodium fluoride. This one would be calcium, and not oxygide, it's oxide. This one's one of my favorite. Barium iodide. That's what you tell the undertaker. Barium iodide. Okay, that's terrible. I know you're laughing at home. This would be lithium is Li, and then sulfur would go to sulfide. This is aluminum and phosphorus, so I'm going to call it aluminum I'm not going to call it phosphoride, I'm going to say phosphide. That tells me that's not spelled correctly, but that is spelled correctly. And then this last one would be K is potassium, and then this would be nitride. Okay, so I hope that gives you a clue as to how we're going to do our naming for the homework.